Okay, so this is going to be the beginning of the section, section 4 about Schrödinger's equation, but in 3 dimensions. So we are going to discuss here how we split this equation into several equations, into 4 equations actually. So let's start. So this is the beginning of chapter 1, is the section 4.1, and we're going to start with the usual Schrödinger time-dependent equation, right? So that it is, where this psi, this wave function depends on x, y, z, and time, okay? So we can rewrite this equation like this. As we said, the psi depends on x, y, z, and time, very well. The Hamiltonian, again, has kinetic energy and potential energy, but the kinetic energy and the potential energy is in 3 dimensions. So that means that we have px squared and py squared and pz squared. And the potential, well, the potential can depend on x, y, z. You could, in principle, even depend on time. Okay, so this is the equation. Now, we are talking about quantum mechanics. So if we are talking about quantum mechanics, we know that momentum is an operator. So that means that the px is actually h bar over r I derivative in x. Same thing for the y, but derivative in y, and z derivative in z. So we can rewrite that equation. Since we know we are dealing with operators here, we can rewrite that equation like this. 1 over that, well, h bar squared, no, the p, x, y, and z, they are square. So we have h bar squared. We have the 2m that was already here, so 2m. Because of this I here, we are going to get a minus sign because of the I squared. And then we have the 3 second order derivatives. Okay, all acting on the wave function and that potential on the wave function. Okay, so things now that are very useful. First thing is, we are going to rewrite this using just this symbol, no? The Laplacian makes life much easier than writing all those terms. And the second very important thing that we are going to do will be dealing with potential energy that do not depend on time, just as we did when we are doing the beginning of chapter 2. Because the potential does not depend on time, we are going to be able to split this equation into 2 parts. One that depends only on space, and the other one that depends only on time. This is something that we already did in chapter 2. And so here I'm just going to go for the splitting scenario, no, the result of that splitting. So the part that depends only on space will be minus h bar square over 2m, the Laplacian. Now this psi depends only on x, y, and z. Then we have the potential, psi, and the energy, right? And the other part of this story is the one that has the energy, right? So this part that has just the energy is the one that gives us that exponential involving energy and time, okay? This means that our wave function, x, y, z, and time, has 2 parts. The solution for this spatial part, which is the little psi, x, y, and z, and what we got here, the exponential that depends on time. Okay, and as we know, we have many solutions, right? So we put this index n. And so these are the stationary solutions. Very good. So this was the first splitting of the equation. Now we'll go to the next step. And the next step, we'll be able again to use separation of variables because we are going to be dealing with potential that are called central potentials. So let's write this here. We'll be dealing with central potentials. What are central potentials? Potentials that only depend on the distance from the origin. They do not depend on the angle. And because of that, it's now going to become more convenient to work with spherical coordinates instead of Cartesian coordinates. Okay, so let's remind ourselves about spherical coordinates. So the Cartesian is here. We have z, y, and x. Right? And if we want to indicate a certain point P here, we could use the components x, y, and z, no, Cartesian coordinates, or we could use the spherical coordinates. So what does that imply? Well, we have the distance, this r. No? So r, so let's write this here. R is the radius, and the radius can go from 0 to infinity. We have the angle theta here with respect to the z direction. This angle theta is the polar angle, and it can go from 0 to pi. It's important to know these ranges because we need that when we are doing integrals for normalization or to find the expectation value. So it's important to know the range of these spherical coordinates, okay? And when we do the projection here in this XY plane, we also identify this angle phi. And this angle phi is the azimuthal angle, and it goes from 0 to 2 pi. Very good. So this is the spherical coordinates, and why they are more useful? Because of what we said, the potential. Well, in principle, it could depend on all three coordinates, but we are only going to be dealing with central potential, so it does not depend on the angle. It depends only on the radius, okay? So let's use spherical coordinates. So we are going to just now rewrite the time-independent Schrödinger's equation. So let me put here the time-independent Schrödinger's equation using spherical coordinates. So the time-independent Schrödinger's equation is this one in blue. And we are going to rewrite the same equation, but now in spherical coordinates. So let's bring this equation to where we are. Okay. And let's write it now using spherical coordinates. So it becomes a little longer because we have many terms, but it will be derivatives in r, in theta, and phi. So let's write it. Minus h bar square over 2m. Now comes the part that depends on r. ddr, r square. Okay. Then we have now the derivatives in theta. Just be a little patient. We'll get through this. And then the part that depends on phi, the derivative in phi. Then comes the potential and the energy. Okay, so as we said, what we want to do is take advantage of the fact that the potential only depends on R and try to now split this equation into two parts. One that will depend only on R and the other one that will depend on the angles. So how can we do that? We are going to rewrite our psi, which depends on R, theta, and phi, into with two parts. One function that only depends on the radius, and the other function that depends on the angles. Okay, so let's do that. So wherever we have the psi, we'll have to now write function of R and function of the angles. So let's see how we can do that. Perhaps we can copy this whole thing again. We don't need to rewrite it. And wherever there is this function, we are going to write R and Y. Okay, so let's start by doing this. Here, we are going to put Y, but Y does not depend on R. So let's put this Y outside. And here we are just going to keep the function of R. Well, since this is just a function of R, this derivative is no longer partial. Right, so we have here ddr. Good. Now let's go to the next term. Again, the same thing. We are going to write this psi with R and Y, but R is function only on R, does not depend on the angles. So we are going to put it out here. This function R is out. And inside the derivative, we will have just the Y. And well, the derivative remains partial because the Y depends on two variables, theta and phi. And well, now the last term, again, we are going to put the R outside. And inside, we keep just the Y. In the derivative, we keep just the Y. Okay, now the rest of the equation here has R and Y equals energy R and Y. Good. Okay, so have a look at this first term here. Most of it is R. The intruder in this story is this Y. So we are going to divide the whole equation by Y to get rid of this Y. Now let's look at this second term. Most of it is theta. The intruder is the function of R. So we are going to divide everything by this function of R. Let's start by doing that, and then we'll discuss some more. Okay, so I'm going to divide the whole equation by R and Y, by R and Y, by R and Y, by R and Y, R and Y. Okay, so let's get rid of the terms. This Y is gone. This R is gone. This R is gone. Here, everything is gone, right? Okay, but there is still one annoying thing in this story, as you can see. This little R that is showing up here. We wanted these terms to have only angles. So we are going to multiply the whole equation by this little R square. Okay, so let's put it here, little R squared, R squared, R squared, R squared, and R squared. Okay, so with that, we get rid of this R squared. So now, this term is only involving angles as we wanted. Okay, and just one more thing. What we are going to do is, look, there is this whole constant, this fraction here in front of this whole term. So we are going to multiply the whole equation by minus 2m over h bar squared. So we get rid of this term. Okay, so we are going to get rid of this term, but careful, because it will show up in front of the V and in front of the E. Okay, so here we have minus 2m over h bar square, and here again. And don't forget, we had included this little r square. Okay, so now let's organize this mess that we have here, right? So the first term, the term that depends only on the radius, what survived there? Well, we have the function of r here. Okay, so I'm going to rewrite as 1 over this function of r, the derivative in r, correct? Now I'm going to bring close to this term also the potential part and the energy, because they involve the little r squared. The potential depends on r, and we multiplied it also by this r squared. And this term of energy is also multiplied by r squared. So I'm going to put everything that depends on radius together. Okay, so here I'm going to put this minus 2m r squared over h bar squared. So I'm stressing that we should not forget that we multiply the v and the e by all that. And so we have here the v, that is a function of r, minus the energy. And that's it. This is the part that depends only on the radius. What is next is the part that depends on angles. So what do we have that depends on an angle? Look, there is this function y surviving the denominator of both terms. Okay, so I'm going to start by writing this, y. And then what else we have? We have 1 over sine of theta. We have the derivatives in theta. Right? And now the part that will involve the derivative in phi. Very good. Okay, all this equal to 0. All right, so this whole part here only depends on r, not on radius. This whole part here only depends on angle. So how can a function that depends on r plus a function that depends on angles give us 0? The only way is that we have a constant here. Okay, so just as we did when we split in chapter 2, when we split the function part that was space and the part that was time, here again we are splitting them. And what is the splitting connector is a constant. So what is the constant? I'm going to call it L plus 1. L plus 1. For now, it's just a constant, just as when we did in chapter 2, we call it E. It was a constant. Later on, we found out that that E was energy. Here is just a constant, it's L plus 1. We are going to learn later on that this is related to angular momentum, okay? But for now, it's just a constant. So we have our 2 equations. Let's then write them, right? So we have this equation here is the radial equation. We are going to copy it here, okay? So this radial equation is equal to L plus 1. We will have to solve this equation. We'll do that. When we solve this equation, we are going to get the part of the function that depends only on r. And then we have this other equation here, which is the equation, it's the equation that depends only on the angle. So let's copy the whole thing here, and we put it down there. And this is equal to, careful, there is a minus sign in this story, so don't forget. Here, I forgot. So there is a minus sign there, no? So that's the only way for us to get 0 there. Okay, so this is a minus sign L plus 1. And when we solve this equation, we are going to get the part that depends only on the angle. Well, but to solve this equation, there is one more detail in this story. This equation, this is an equation for a function of two variables, theta and phi. Can we split? Yes, we can. We can split it and to make the solution, to find the solution in an easier way. So before we split, let's manipulate this equation a little bit. So what we are going to be doing is the y, the function appears in the denominator here. Well, let's make it disappear from the denominator, which means I'm going to multiply this whole equation by y. Okay, so multiply the whole equation by y. And the other thing that we are going to do, multiply the whole equation by theta squared to remove the theta squared that we see here in the denominator. Okay, so our equation is now going to become, this equation will become sine of theta, because of that, we have this sine of square and this sine here. So now we have now just sine of theta, and then the derivatives in theta. Okay. And you see that this y disappeared. Okay. The second term, no theta at all. And so we have just the part in phi. And on the right side, minus L plus 1. We multiplied everything by sine square, so there it is. And we multiplied everything by the function. So you see, why are we doing this? What is the motivation? Because now we see this term, only theta is contained, right? Well, apart from the function, but you see thetas appear. And this term has only phi, has only the derivative in phi. So this will help us splitting the equation. How are we going to do the split? We are going to use separation of variables again, no? So we are going to write that function of theta and phi, no, the y, we are going to write into two pieces. One part that depends only on theta, and another function that depends only on phi. Okay, so let's rewrite that equation that we have above, but now instead of putting y, we are going to put this this product. So since I'm a little lazy, I'm going to copy this. Oops. No, I'm going to copy just this term first. Okay. So I'm going to copy this first term. And as we said, wherever there is y, we are going to put the function of theta and the function of phi. But this derivative is only theta. So the part that depends on phi comes out. And what survives here is just the part that depends on theta. And this derivative is no longer partial, because now we only have theta. Very good. Now, the other thing is, I'm going to bring close to this first term, this term here, because this term is all theta as well. And so I'm going to pick this term here and bring it here to the left side. And when I do that, now this sign becomes plus, right? And the y, as we said, we are going to write it as the two functions of theta and function of phi. Okay? All right, so this part, most of it is involving theta. there is the last term that we have is this one. From this is just phi, so the term that depends on theta will come to the front. And now that derivative becomes, is no longer partial derivative. It's the derivative in phi. Okay, so, oops, sorry. This is the function of phi. And this is equal to 0. Okay, so this first term, now this first term here is all theta apart from our annoying function of phi. And this term here is all phi apart from the annoying function of theta. So we are going to divide the whole equation by the product of theta, the function of theta and phi. Function of theta and phi. Function of theta and function of phi. Okay, so that eliminates the intruders. So here we got rid of all. And you see that this whole term here now really only has theta. And this whole term here now only has phi. For this sum to give us 0, then we know for sure that we have to have a constant. So this is going to be constant m squared, and this is going to be constant minus m squared, so that we get 0. So we finally found the two last equations. Okay, so the two last equations are the one that depends only on phi and the other one that depends only on theta. So let's write here the one that depends only on theta. So this equation becomes, look, there is this function phi here, but I'm going to multiply the whole thing by that function. So the equation becomes sine of theta, the derivative, sine of theta, the derivative of that function of theta, then plus, here we have L plus 1 sine square of theta. All that multiplied by that function, because there was, the function was here, but now I'm multiplying this whole part by this phi, this equation, this function of theta. And there is, this is equal to m squared theta. Okay, now what I'm going to do is I'm going to bring this m squared to the left side, and we have this equation here. So this is our equation just for involving only theta, okay? And the other equation is the equation involving only phi, so we are going to write it here. So this is equal to minus m squared and the function. Okay, so these are the two last equations. Okay, so let's mark all of the equations that we obtained. This is the equation involving only phi. This is the equation involving only theta. Okay, once we solve these two equations, we are going to find from here, we will see this more in more details, but I'm already going to tell you. This will give us an exponential of phi. This will give us a solution that involves theta. Okay, so this is the solution here is known as associated Legendre's function. I'll just write the solution, but we are going to be discussing this later. Okay? So these two together gives us that function of theta and phi, which are known as spherical harmonics. And we'll talk more about them. Okay? But for now, all that we are saying is we have this equation for phi, this equation for theta, and in the beginning, we had this equation, the radial equation for r, and even before that, we had the energy. And so combining all this, we will have our wave function. And so the wave function depends on r, theta, phi, and time, right? So we have an equation to get the function of r. We have an equation to get the function of the angles, which we said is they are called spherical harmonics, and we already found the part that depends on time, which is this. Okay, well, we'll talk much more about this.